Morning, everybody. You guys are awful quiet this morning. Must be something exciting happening on the internet. Right? Everybody's looking at their phones. Does everybody have a lens, a magnifying glass? Yeah? Okay. We're going to need them. So, what we're going to do today is we're going to apply everything that we've learned about refraction to the special case of, well, a lens. And this is going to take us basically all week because these things are just way too cool. And so I've given you a magnifying glass for some experiments we're going to do here in just a little bit. But I want to start by tackling kind of what we're going to do and some of the simplifying assumptions we're going to make for this class. Lenses come in lots of different shapes and sizes and configurations. We will limit the configurations we're going to do to the two that are on the screen. But in truth, like anybody that wears eyeglasses, okay, the shape of the lens can be like sort of concave on one side and then convex on the other. They can do all kinds of strange things. And depending on what it is that we're trying to pull off with the optical system. We will simplify and make sure that we only talk about a converging lens and a diverging lens. And what those terms refer to is what the lens does with the light. In the top case, all the light rays that are moving parallel to the optical axis get focused down to the focal point. And for a diverging lens, they get spread away from the focal point. Notice, right, that these focal points, well, as we're about to find out, lenses are going to have a couple of focal points because they really have two sides, two curvatures to them. We'll stick to spherical lenses, and we're going to apply some pretty simple mathematics. It turns out the equations I'll give you do come from Snell's law, but there's lots of derivation and geometry that has to go into it. And we will give you just the punchline. Again, we are going to employ the simulation. We're living in one, so why not use one, right? Let me get it open. Let's see, let's just jump into the simulation right now. Okay, again, link is on Canvas, and I encourage you to go into this and play around so you get a feel for what the different possibilities are when it comes to lenses, right? You've got to set this up so that we have an arrow. We want to use the principal rays. We can make it look bigger if we want. Nothing else really needs to change. We can go ahead and put the labels on. But first off, right out of the bat, right, notice that there are two focal points for a lens. In fact, in a lot of optical diagrams, we don't put the shape of the lens or the mirror in. We just draw like a vertical line that represents the plane that the optic is sitting at. And we can tell at a glance if it's a mirror or a lens based on the number of focal points. If it's a lens, there's going to be two focal points. One on the front, one on the back. If it's a mirror, there'll only be one focal point. But it's easier to have the shape here to remind us about what's going on. At the top of the simulation, you can switch between the two different kinds of lenses, just like you could switch between the two different kinds of mirrors we had last time. And we can go ahead and drag the object around, and our rays will get traced for us. If you've heard of ray tracing in video games, this is what's going on in three-dimensional space with every light source in the scene. Okay, it's actually, computationally, it's a miracle that a GPU can actually pull this off with any kind of speed and efficiency. So it's pretty darn amazing. All right, so let's take an object, right? I'm going to kind of lock its height here so I can just slide it along the optical axis. Let's do like the regimes, right, or the different possibilities for a converging lens, right? I've got my object sitting out here. It's outside the first focal point. And what kind of image are we getting? It's inverted. It's real because they labeled it as such. Let's take the labels off so that we get a little bit more practice here, right? How do we know it's real? What are the real rays doing? What's it called when they all come together? They converge, right? They leave the tip of the arrow and then they reform. And that's got to be the tip of the image that is formed. Because real rays have all converged and come to a point, it's got to be a real image. It's inverted, it's real, and it's magnified or reduced? Reduced. Okay. So that's with it kind of far away from the focal point, right? As we come in toward the focal point, what's happening to the magnification? It's increasing, isn't it, right? And you can see here that we've kind of gotten to a point where it's about the same size and then it kind of grows to be bigger. So there seems to be like a regime where it's smaller and then another regime where it gets bigger. And the point at which they're about the same size looks like it might be twice the focal length. And from mirrors, we knew something about twice the focal length. Remember what it was? The center of curvature. Like, remember, these spherical things are sort of cut out of a big sphere. That's not actually how we do it, but that's how we model it. So about twice the focus, you're going to get the same size. Anywhere closer than that, and you'll get a magnified image. Anything further away from that, you'll get a reduced image. But is the image still real? Yes. Still real, still real, still real, still real, still real, real. Ah! And then when we get to the other side of the focal point, what happened? Okay, so notice it flipped to the other side of the lens. We'll get into front and back in the sign conventions in a second. But it flipped. The image was on the other side from the object, and now it's on the same side as the object. It's also, what is it, upright or inverted? It's upright, and it's magnified, and it's real or virtual? It's virtual. Have you noticed something about the virtual images in our single element system? In other words, one mirror, one lens. Is there a pattern that's kind of emerged about virtual images versus real images? What?
Is it because they're in front of the focal point?
It's a little bit simpler than that. This real image is inverted, isn't it? But this virtual image is upright. And when we were doing mirrors, the real images turned out to be inverted, and the virtual ones turned out to be upright. I hesitate to tell you that or teach you that or let you know that. You have to be careful with that information. If there's more than one mirror or lens in your system, that rule does not hold anymore. Okay? But for single lens, single mirror systems, pretty much, if it's upright, it's virtual, right? And if it's real, it's going to be inverted. So that's kind of handy. But you can see here that no matter where I put it in front of inside the focal length, it always stays virtual, right? Okay. And then we can switch to the diverging lens. Diverging lens is even less spectacular because no matter what you do, the image is always what? It's always virtual. Do you see the dotted lines that are being drawn? Right? All the rays here on the back side are all diverging. They can't ever come together again. The only place that rays converge is by using virtual rays, drawing from real rays backwards to a point of convergence. So it's got to be a virtual image, it's upright, and in this case, it's always reduced. Right? Okay. So there isn't, for diverging lenses, there's really only one answer, right? For a single diverging thin lens, it's going to be upright, it's going to be reduced, and it's going to be virtual. Okay? The trick comes when we have our converging lens. If we're outside the focal length, what kind are we going to get? Real or virtual? Real. And if we go inside the focal length, what are we going to get? Virtual. Okay. All right, so play around with that. Try to get a feel for it on your own. It's kind of vital information to have in your brain, and those of us that learn with kinesthetic learning, it can be a real handy thing to kind of set these regimes up. All right, let's dig into just what the heck is going on here. Did you bring your sign convention sheets? Yes, no? Oh, yeah, okay. Those of you that have come in that haven't gotten a magnifying glass, you're going to need one in a second. So I'm going to give this out, pass it along the rows, make sure everybody gets one. Let's see, we're going to meet in the middle here because I'll start some here at the back. But again, if you did not get a magnifying glass, make sure to grab one. I need these back, right, when we're done. But we're going to need them in just a minute. All right. What I consider the second hardest part of optics. These sign conventions, I've warned you before, they can get you, right? If you're not paying attention and you're not using them carefully, you can get very thrown off depending on what signs are being put on object distance, image distance, magnification, all that. So notice there's a change here, okay? From mirrors to lenses, there's a switch, okay? Objects for a single lens system will always have positive distance, and I'll show you some pictures in a second, okay? But notice the distance to the image. When we did mirrors, if the image was on the front side of the mirror, what sign did we get?
Positive.
We got positive. But look here, on a lens, if your image ends up on the same side as the object, because the object is always sitting on the front side of a lens, what sign are we going to put on it? Negative. It's backwards, okay? So you have to be really aware. You have to be paying attention. It's not just plug and chug, it's getting these sign conventions correct, right? So if a problem tells you that the image forms on the same side as the object, and they give you that image distance, they may not give you a positive or negative. You have to be able to go, oh, it's on the same side, therefore it has to be, negative. So obey the conventions, right? For the focal lengths, converging is positive, diverging is negative, magnification stays the same. I, again, tried to make it easy for you so you had a static reference. These are both converging lenses. The only difference between these two pictures is where the object is located in regard to the focal point. One you can see is very far away, right? So you end up with a reduced image. The other one I put a little bit closer to show that you can get a magnified image, right? It just really depends on how close this object gets to the focal point. So let's just define a few things here visually. Focal length, the distance. So the optical axis sits in this dotted line right here. And then there's the plane where the lens is located. I probably am only going to draw just vertical lines in my pictures. But the distance, the focal length, is the distance from the center to wherever the focus is, right? That's F, okay? Which side is the front side of this top lens? Yeah, this is front, okay? This is back. I'm not leaving permanent ink on this one because I want you guys to go through the process. The object distance, the distance from the lens to wherever the object is, right? Down here, it would be that distance right there. Notice two focal lengths. We will always keep these equal. They'll be the same on either side. So if you're told that you have a focal length of 35 centimeters, it's going to be 35 to the left and 35 to the right. Again, front being wherever the object is located. So let's take a look at the equations, right, for working with lenses. So this isn't necessarily just a converging lens. In fact, You know what? Let's go back to the sign conventions page. I'm just going to write it right on here. And you're probably not going to have to write anything because it's already on your page, I'm going to guess. Have you seen this equation before? Yes. What was that one for? It was for mirrors, wasn't it? Turns out exactly the same equation applies for lenses. So this is where the slippery slope is, right? Same equations. In fact, the magnification equation is the same, right? We don't use center or radius of curvature very much in lenses, but you have the same equations for mirrors and lenses, but a different set of sign conventions. So sometimes you get lulled into this idea or this false sense of security. Oh, well, the equations are same, so the conventions are the same. And you fall into this trap of thinking, oh, well, object distances are always positive because Mr. Balogh said we never do anything more complicated than that. Oh, so therefore image distance is positive when it's on the front side. That is not true, right? That's only true for mirrors. That is not true for lenses. So I'm like begging you, right? Pay attention to the sign conventions, right? You don't have to memorize them. What you have to do is put a Post-it note in your brain that says, whenever I am working with mirrors or lenses, I have to pay attention to the sign conventions. Whip out the sheet, whip out your cheat sheet, whatever, right? And make sure that you are double checking against this table right here. So let's do a couple problems here. I'm going to rely apparently on my classic focal length of 15 centimeters. And we're going to do a converging lens, right? So if I've got a converging lens, what do I know? If I'm told the converging lens has a focal length of 15 centimeters, what sign am I going to put on that focal length? Look at the sign conventions. What is it? It's positive, isn't it? Again, I was told it was a converging lens, and then just 15 centimeters, I have to know to put a positive sign on that. Don't let a number go by in optics without you figuring out if it's positive or negative. And if it's positive, put a positive sign down. Don't just leave it. We have a tendency for positive things to not have a sign on front of them. That's an indicator to you, to your brain, to future you when you're going back and studying that, oh, okay, I thought about that. You might have gotten it wrong at that point, but at least it's an indication that you thought about it. We're going to go for an object distance of 25 centimeters, and then image height is 10. These are kind of numbers that I used before. But let's calculate where the image is going to form. And of course, in the homework, you might be given image distance and you're asked to find object, or you give an object an image and you're asked to find the focal length. You can solve for any one of these things, right? I'll just be solving for image distance. So what are we going to do for like our basic little like picture, right? Always like visualize something, okay? Even if it's a little sketch. I usually draw, when I do lenses, I usually draw this. I draw the optical axis and then I just draw a straight line for the lens. You can, if you want to, draw the shape of the lens to help you remember, right, what kind of lens you're working with, but the actual shape of the lens doesn't matter. I usually just put plus F. And then you got to drop a couple focal points in your sketch. Are we inside or outside the focal length of this lens? We're outside, right? So our picture is going to be something like this, isn't it? Right? I'm not going to draw the rays. But we're in this type, like you refer back to a picture, a ray diagram that either somebody's drawn for you or is in a book or comes from the simulation, right? And I'm looking at this going, okay, it's going to be one of these two. It kind of depends, right, on how close this object is to the focal length. But I know, like I can see in the picture, right, that for objects outside the focal length, What kind of images are we going to get? Real, inverted, and then it could be magnified or reduced depending, right? I wouldn't be surprised to get either of those things. So this little picture, right, means that I'm going to guess it's going to be real, it's going to be inverted, and my magnification is going to be it depends. So let's go ahead and calculate some stuff, right? Image distance. I'll do the algebra once. 1 over f equals 1 over do plus 1 over di. Move the 1 over do over. 1 minus f. 1 over f minus 1 over distance to the object equals 1 over distance to the image. We invert both sides of this equation, which gives me my image distance is 1 over f minus 1 over the distance to the object, and I've got to invert that whole thing. Sometimes it can be hard to remember too. It's kind of like resistors in parallel, right? You got to remember to do the 1 over f, 1 over f, 1 over f. So 1 over positive 15 minus 1 over positive 25. Objects are always positive distances. And then I invert that. And if I did that right, I got 37.5 centimeters. It came out as a positive number. So we check back to the sign conventions. What does a positive number for image distance mean? Means it has to be on the back side of the lens. Is it? What side of the lens is this where the object is? This is all the front. Do our images end up on the back? Sure do, right? So I'm feeling confident about that calculation. I know, right, that it has to end up just like my picture said right here, my little sketch, okay? All right, magnification. Maybe. Negative di over do. That's a negative of a positive 37.5 over 25. Got me negative 1.5. Okay, so what does the negative sign on the magnification mean? It's got to be inverted. And in fact, we saw that from our ray diagram, right? And so I'm happy with the minus sign. In this case, 1.5, what does that mean? Is it magnified or reduced? It's magnified, right? 1.5 is 150 times bigger, right? So this thing, since it's a height of 10 centimeters, would end up being an image height of like 15 centimeters. So what that means is that we're like in this regime right here, right? Where the object's close enough to the focal point so that it's magnifying the image. The difference between these two pictures here is kind of subtle, right? It's just a function of how far away you are from that focal point. So you can end up with either or for the magnification. All right, let's get another one of these pages. Let's do one where the focal length, again, is positive 15. So if I tell you that it's positive 15, you know it's a, what type of lens? Converging, according to our sign conventions. It's a converging lens. Our object distance will now be 10 centimeters. Okay, so where are we at now? Yeah, so if I drew a little sketch of what's going on, I've got my focal points on either side of my lens. My object is now inside this focal point, right? And I have to go find, here's a picture, okay? So here in this picture, I've got a converging lens. My object is inside the focal point, and in playing around with the simulation, I learned that there wasn't any other possibility for this, right? I'm always going to have an upright, magnified, virtual image. Okay? So I can, in my sketch here, and do something like, well, it comes up like this, right? And it's upright, it's virtual, and it's magnified. Okay, so let's calculate that. We're just going to go distance the image because we've already solved for it many times. So 1 over positive 15 minus 1 over positive 10 inverted got me negative 30 centimeters. Okay, what does the negative sign on the image distance mean? A negative sign means it's on the front side. Is that true? Yeah, right? That's what it should be. The front side is where the object is. Should have a negative distance. All right, I like it. Magnification. Negative, a negative 30 all over 15. That looks like 2, doesn't it? 10. I put the wrong number in. What mistakes are you going to make when you're doing optics? Sign mistakes, number 1, and then number mistakes, number 2, right? Because I just did it, right? This turns out to be positive 3. What's the positive sign on the magnification mean? It's upright. And the 3, what does that mean? It's in fact, it's 300% or 3 times bigger than what it needs to be. Okay, time to experience this. Where did the lenses end up? I started passing out the boxes. Where'd the boxes? Oh, they're over here. All right, does everybody have a magnifying glass? Who needs one? All right. You got to be careful. Don't hit the person next to you during the following exercise, right? What I need you to do is take one of these magnifying glasses, okay? And you need to find a faraway point in the room. If you're in the middle, try to look outside. If you're over here on one of the sides, you can look across the room. But what you're going to do is you're going to hold your magnifying glass out at arm's length, and you're going to look at something that's far away. Okay? Again, don't hit each other. It does need to be kind of far away from your face, but you're going to look at something far away. It could be the outside. It could be the screen, probably. I wonder how far away we have to be for that to work. Yeah, don't look at each other. Okay? Yeah, it works if you're sitting in the back and looking at the screens, right? What do you see? Is it upright or inverted? Inverted. It's inverted, okay? Is it magnified or reduced? Kind of looks reduced, doesn't it? Although it's messing with your brain, isn't it? Okay? Is it real or is it virtual? You're looking at a real image. Okay? In fact, this image is forming somewhere right here. So what side is the front side of your magnifying glass? Is it the side that's closest to you or the side that's furthest from you? It's the furthest side. The objects we're looking at are way out there, aren't they? Okay? And so the front side is out there. This is the back side of the lens. And we are in this regime right here, right? This object's far away from focal length, right? Where's the image being formed? Somewhere on the back side of the lens, which means the image you're looking at is like somewhere in here. Your eyes are trying to focus on something that's sitting right there. Okay? Now take your magnifying glass and get really close to your notes or your phone or your hand or something, right? Use it the way that you've been taught, like every normal person that's not borderline psychotic like your physics teacher, right, would use it. Now what do you see? Upright, magnified, virtual. So you can see a virtual image if you use the magnifying glass like a magnifying glass, but then you can also see a real image if you hold the magnifying glass out at arm's length. Okay? So how do you tell the difference between a real and a virtual image? You really can't, right? because it's a single lens system, because we only have one lens, right, that we're using, and I've already told you kind of the broad strokes for if it's inverted, then more than likely it's a, what kind of image? Real, okay? So again, for single lens system, it's kind of a dead giveaway. If it's inverted, it's real. And if it's upright, it's virtual. And is there anything in your brain that's telling you that that's the case? No, right? The virtual image, in fact, tends to look more real than the real one, right? Mostly because you're not used to seeing real images through lenses like this, okay? Especially those of us that wear glasses or contact lenses, which we're going to get into later, okay? Maybe Thursday, right? So I wanted you to be able to kind of experience and feel the difference, right, between a real and a virtual image. I'll probably forget, but I do need you to hand those in when we're done, okay? But you can kind of mess around with them.
For the last equation, how come we didn't have a height?
Because height, okay, fine. What height do you want? 5 centimeters. So therefore, the image height is 15 centimeters. Right? You just take whatever the height of your object is and multiply by the magnification to get the image height. Generally, to tell you the honest truth, in optics, we're not really concerned about we want to know the magnification. We don't care what the actual height of the image is. We would only start to worry about that if we had to be sure, like, we have to form the image on a certain screen size, or like these projectors, okay? You have to be very careful about how big you make those images. These are real images, and I can tell because real light rays are present. I can cause a shadow to happen. And so in the actual lens apparatus, I forgot to bring my camera lenses today, darn it. In the lens apparatus, they have the ability to sort of alter where those lenses are located, so they can, like, I don't know if you've ever messed with a projector, but you can make this like picture really big so it's spilling over the edges of the screen, or you can make it small. We call it zoom, but there's you can build in ways to make sure that your images are the correct size for any kind of projection. It's really the magnification that matters, though. So, all right. And this was what I had in case everything else failed and I forgot to bring the lenses and all that kind of stuff. Anyway, so let's do the diverging lens, okay? So if I told you that the diverging lens had a focal length of 15 centimeters, what are you going to write down for the focal length? Negative, right? Again, it's tricky because it's just words, and you got to make sure that you remember diverging means negative focal length. Let's drop the object at 35 centimeters and solve for the image distance. Is this math hard? No. It's fractions. You do it in your calculator, and the hard part is getting your calculator not to lie to you. 1 over negative 15 minus 1 over 35 inverted gets me negative 10.5. I failed to draw my picture. Remember, diverging lens, you're going to be putting the, it doesn't actually matter where you put the object. This can be the object. The image is always going to be on the same side as the object. Where did the picture go? Right here. Okay, so here's my sketch. Object, image is always going to be a virtual image. There's no other case where it's not. And so diverging tends to be pretty simple. It's almost always the same picture. And that's negative 10.5 centimeters. Don't forget your units. I grade myself. I give myself an F every time I miss one. And then, okay, so what does the negative sign mean, though? Like when you get the image distance is negative, what does that mean? It means on the same side as the object, which is true, right? This is the sketch that we've got. All right. And then magnification, mind your minus signs. put in the right numbers. 35 gets me, I got, this is like 0.3, okay? And it's a positive 0.3. So the positive sign means what? Positive sign means it's upright. Its orientation is upright as opposed to it being inverted, flipped over. And the 0.3, it's smaller, right? It's roughly 1/3 as high as it used to be, right? A third would be 0.33. So 30% its original height. Okay, so in review, what do you have to be careful of? Signs, right? Signs. Those sign conventions, they matter. There's a process that I've been trying to teach you where the equations, the sign conventions, right? These, where is it? Right there, right? These sign conventions, these equations, and these pictures all work together to allow you to predict what's going to happen, but also check what is going to happen. Like in optics, it should be really hard to make a mistake. Like really, like let's say that you forget to put a minus sign on the focal length for a diverging lens, right? If we went through here and we did this math for this problem right here and we forgot to put in -15 right here, okay? And this ended up being a positive number, right? Well, 1 over positive 15 is bigger than 1 over 35, isn't it? So if you take a bigger positive number and subtract off a small number, it's still going to end up positive, isn't it? In which case we would have gotten this positive number, or something similar to, maybe not the same number, but we would have gotten a positive sign, and then we look at the picture and we know instantly something's gone wrong. We know it has to be negative because the object and the image have to be on the same side. So, yes, the sign conventions are important and they're where you're going to mess up. But if you're using the visualization, the pictures, right? And you've played around with the simulation so you know kind of where those pictures are coming from and what's going on. If you check the picture, you check the math, they should agree. And if they don't, something's gone wrong somewhere. And then you got to go and troubleshoot. Okay? It's actually kind of, I think one of the things that drew me to optics in graduate school was this concept and idea that no matter how stupid I was, eventually I could get it. It was like it was built in, right? The math and the pictures and the science, everything had my back. So even if I screwed up, it would sort itself out, right? As long as I was careful and stuck to the process. It's when I ignored the process. It's when I started thinking, oh, I'm really good at this. I can ignore the pictures and just do the math. Boom, I was dead, right? So use that sort of holistic approach and check yourself. Okay, so we've learned the basics of optics, ray optics, okay? In that we've conquered mirrors and also lenses. How you doing? Are you doing okay? Like compared to electric and magnetic fields, how are we doing? Okay. This is good, right? You got I might actually understand what's going on. And so now you're afraid because you haven't understood anything in this class up to this point, right? No, you can understand optics. It's good. Now we're going to move into, we're going to do calculations, but the next part here is largely conceptual in the sense that we're going to apply what we know about optics to everyday optical systems. Cameras, the eyeball, and that's going to take us into how do we correct vision, like what are some vision problems, and then how do we help people see clearly. We're going to apply this, and the difficult part, again, is keeping track of what's going on in the problem. We're going to fall back on our process of pictures, math, checking each other. But there's a lot of terminology that starts coming out, especially when we start talking about eyeglasses. Let's conquer cameras first. At the risk of sounding old, something has happened in my lifetime that I never could have expected growing up. Growing up, I was into photography. I actually developed my own film in middle school and high school. I did the yearbook photos for a lot of our sports teams. I was really into it. And it never would have occurred to me that people would carry cameras around with them everywhere all the time, right? And nowadays, we just have this kind of photo culture, don't we? Right? It's like pics or it didn't happen. And now, well, pics, is it AI or not, right? Right? It's just, it's kind of crazy to think about how well we can document the world around us. Because in its essence, photography is documentation. It's capturing moments in time. It's capturing history. What's the best camera?
Still film.
Nope. No, there's only one answer to this question.
The one that starts with an H.
Nope. Not a Hasselblad, although those are great cameras. The best camera is the one that you have with you. Okay? Full stop, right? Because if you don't have a camera with you, there's no way to record what's going on, right? Okay? So don't let anybody tell you, oh, your cell phone camera is not a real camera. It's a camera, and it's probably the best one that you have, okay? I gave up my SLR cameras about 10 years ago. About 10 years ago, I noticed that cell phone cameras were about 90% as good as a SLR camera, and I could carry it around in my pocket instead of in a backpack. Because I had the camera body, I had 4 different lenses, I had filters, I had all of that. And could I take really good pictures of flowers and landscapes? That was always my thing. Flowers and landscapes. Taking pictures of people I didn't like. But like taking pictures of landscapes and flowers and stuff, mostly because like I was able to go walk somewhere to take the picture. But like, were the pictures better with my SLR and my fancy lenses? Yes, they were. But they weren't that much better that it, because I would always get a sore back if I was carrying my camera around with me, right? I'd go on a trip and I'd be packing my luggage and there'd be a whole luggage that was nothing but camera. And so here I am paying an extra baggage fee just to bring a camera along when I can get away mostly with this thing, right? So the best camera is the one that you have with you. This picture, being old-fashioned, right, is kind of trying to show you what a camera is trying to do. Camera lenses are highly complicated. They consist of, well, in their simplest form, at least 3 lenses, but probably more like 12, like in a telephoto lens where the lens slides in and out on the front of the camera. Movie cameras are basically the same thing as a still camera, only they just shoot at multiple frames per second. So we have some object, right? And we're trying to capture that object onto film of some kind. Nowadays, the film is digital. It's a sensor that captures the photons, turns those photons into electrical signals that are then stored in the memory card. Back in the old days, it was actual plastic film that had chemicals on it, silver nitrates and others, that would react to the photons. And then you would have to develop that film through a chemical process. But regardless, we need to get an image. What kind of image? Real or virtual? It's got to be real, right? If it isn't real, the chemicals aren't going to do anything and the sensor is going to go, right? Okay, so it's got to be a real image, or at least it has to capture real photons in order for this to work. You notice in this particular setup, the object and the image are flipped. And in fact, even in your phone camera, right, when you're taking a picture of something, in reality, the image that's being formed on the sensor of your phone camera is upside down. So what does the software do? Turns it right side up, okay? In old-time cameras, we had an extra mirror that would flip the image for us in the viewfinder, right? Otherwise, your brain gets really screwed up If everything's upside down, you're trying to chase the football player upside down. It just doesn't work. So it's a complicated system. Lots of mathematics going on inside of the camera lens. But in addition to that, there's this thing called the aperture. And I'm teaching you all of this for a reason. And I have to confess, it has less to do with physics, and it has more to do with a crusade, a personal crusade I have, to elevate the art of picture taking from the absolute trash that it has been for the last 20 years. We've multiplied the number of cameras in the world, but we've done a very poor job of teaching people how to take good pictures. Okay? And so I'm going to teach you a little bit about photography so that you can take your pictures from being whatever they are now, and maybe some of them are great, okay, to like your friends going, oh, you should put that on Instagram or whatever, right? Okay? Like, and it's not, this is the thing, it's not hard. Okay? I mean, photographers work for years to perfect their craft, but the essence and the basics of photography are actually quite simple. The shutter on a camera is kind of the thing that opens and closes to capture that moment in time. But the aperture allows the camera lens to either restrict the amount of light that's coming in or allow more light to come in. We have an analog in our eyeballs. What's the structure in our eyeballs that controls this? The iris, right? We have an iris that can dilate, right? Get bigger, right? Or constrict. And what does it do when it's like really bright outside? It constricts, right? We're trying to limit the amount of light that's entering the eye. We want to do that because it hurts to have bright light shining into our eyes. So we limit the amount of light. A camera, the film and all that kind of stuff, there's this balance between like exposure, how much light hits there, how fast the shutter is going, whether or not you want motion blurs, all kinds of stuff going on. But there's a knock-on effect to this aperture system that allows certain amounts of light in, and it's something called depth of field. Okay? This right here is an absolutely horrible picture. Okay? I didn't take this one, although I do have pictures that look like this. Okay? So why is this a bad picture? It's not what?
It's not centered.
It's centered enough. Centering the subject in the picture is actually not what you want to do. We'll get to that in a bit. This is an awful picture because, number one, it's a picture of something that's duller than dirt. Like, who wants a picture of their driveway? Seriously. But it's actually an excellent picture to teach you about something called depth of field. Notice how in this picture, everything is in focus, right? The bricks that are up close are mostly in focus. The grass is in focus. The street is in focus. The cars are in focus. Things that are really far away are in focus, and things that are up close are in focus. We say that the depth of field in this picture is very large. In other words, things up close, things far away, they're all in focus. So the focus field, the range of distance in front of the camera where things are in focus, it's essentially infinite, right? Things that are far away, things that are up close. That can be a good thing depending on what it is you're trying to do, okay? Now compare and contrast this with this. I deliberately chose pictures, okay, that came out of an example textbook, right, okay? They're both almost the same color palette, aren't they? Right? It's relatively dull colors, some greens, some browns, some reds, some kind of things, right? But if I had to ask you which of these two pictures is more interesting, which one is it? Okay, why? I mean, it's a dead flower. right? Who wants to take a picture of a dead flower? It actually has nothing to do with the subject of the picture, and it has everything to do with a psychological trick that's being played on your brain. How do you know that the flower is the interesting part of this picture? It's what's in focus. You see that? The background of this picture is blurred out, isn't it? Okay. Whereas in this picture, everything being in focus, your brain is left to kind of wonder, well, what was the point of this picture? Was it the bush? Was it the lawn? Was it the car? Right? Everything being sort of equally in focus means that your brain doesn't have a singular subject with which to attach itself, right? Whereas here, it's a dead flower with, I don't know, snow on it? What's on there? It's a picture about the ephemeral nature of life. Everything must die. No! The background is blurred, right? And so your brain instantly edits it out. How many of you thought about the background when I first showed you the picture? Right? You focus, your brain went, oh, flower, boom, picture of flower, right? So depth of field. This is a very short depth of field, or a small or a low depth of field, where the thing that is in focus is singular. In movies, there's something called rack focus. They do this in TV a lot now too, okay? Where you'll get like, somebody will be talking in the foreground and there'll be somebody talking in the background, and they'll start adjusting the focal depth. They'll show the up-close person, and then the person behind them starts talking. They'll rack the focus so that they focus on the back person and the front person goes blurry, and then they'll rack the focus back again when the up-close person starts talking. Okay? They're taking advantage of your brain's attention, right? Focus on the thing that matters in the scene. The way that you pull off this depth of focus in a camera is with the camera's aperture. Wide open apertures have very short depths of field, right? So the aperture that's on the top here, okay, would be used for taking the picture of the flower. But when you start constricting down and you make your aperture smaller, you end up with a very large depth of field. Anyone that's gone to the doctor's office and had their eyes examined and had your eyes dilated, do you remember what happened to your vision for like the next half hour? Everything was blurry, wasn't it? Right? You could not focus. Well, your eyes were dilated, right? Which one of these two were your eyes doing? The top one. What kind of depth of field did you have? Hardly any, right? There was like one point where you could hold your phone and actually see it. Too far away it was blurry, too close, right? Okay. Normally our eyes are rapidly changing, so we tend to see a full depth of field, or at least we think we see a full depth of field. But if you I'm turning the lights on. Let's see if we can pull this off. Sometimes people struggle with this particular exercise, okay? I want you to turn so that you're looking as far across the room as you possibly can, right? So these people need to look over there. These people look over there. If you're sitting in the middle, just turn to one of the sides, okay? I want you to look at something far away. Look out the window. Look out like at the corner or edge of the wall. And then without taking your eyes off the thing that you're looking at far away, concentrate on what's in front of you. Like keep looking far away. Don't adjust your view to the person in front of you, but just sort of try to take in what that person in front of you, are they blurry? Are they in focus? Or are they slightly out of focus if you're looking far away? They're blurry. So what is your brain doing? It's editing out the people that are, it's saying the things in the foreground are not important because, duh, you're looking at something far away. but you tend not to think. You think everything around you is in focus all the time, right? My book's in focus, you're in focus, you're in focus, you're all in focus. What my brain's done there is it's edited together my eyes jumping around, right? And then put that together as a cohesive representation of reality, right? When in fact, the only thing that can be in focus is the thing I'm focusing on, right? Everything else blurs out and your brain stops paying attention to it. And your brain hopes that things don't change while it's not paying attention to it. Because if something does change, say out of the corner of your eye, what does your brain then do? Right? And why does your brain do that? Evolutionary speaking, the tiger's creeping up on us in the grass would cause the grass to move, right? I might be looking at the piece of fruit right there, but the tiger's over there. I need to know that, right? So we're primed, right, for our attention to be grabbed by a sudden change, okay? All right, so depth of field is important. These are more awful pictures about depth of field. Do you see how here the depth of field is very narrow? The matches up close are all out of focus, right? And there's just kind of a narrow range around the coin where it is in focus. And then here, there's like a lot of depth of field. All of the matches, forward and backwards, are all in focus. You'll notice, too, this picture's pretty bright, and this one's pretty dark. To pull off the depth of field, the big depth of field, remember, what do you have to do? Make the aperture really tiny, right? When you make the aperture tiny, you cut off the amount of light that's going into the system. And then the sensor or the film can then struggle to get the proper exposure going, okay? So how do you pull this off in today's modern age? On my manual camera, I had a ring. I would just turn it and I could control the aperture and therefore control the depth of field. If I was taking, say, yearbook photos of people, this is what I would be doing, right? Okay? Why? The yearbook photo, what are we focusing on? Right? Okay? The person. Okay? And so you fuzz out everything forward and back and all that kind of stuff, right? People are always like, oh, take a picture of me. And they're like, oh, but I've got to choose a good background. I'm like, no, you don't. I could take a picture of you in front of a pile of manure and make it look good. Okay? Because it actually doesn't matter what's in the background, right? The only thing that really matters is that it's not a single color thing. You want a contrast of some kind, right? So manure pile next to white wall, I got you, right? We can do a good picture. It won't smell good, but luckily pictures don't capture smell. So on a modern device, and I tested this morning. I want to see if it's going to work, okay? On a modern device, don't worry, I'm not taking pictures, okay, right? But I will make you motion sick, okay? There are ways to control what's going on here. Do you see how I've got video, portrait, or photo and portrait? Okay. Notice what happened on this front-facing camera. Look at the background. See how it's blurred out? Okay. And then if I switch to photo, it goes back to being clear again. Okay. What is portrait mode on your device doing? It's doing a false depth of field, okay? The depth of field that it's, the depth of field that it's doing is in software. It's detecting, was it doing it? Did it show the little, yeah, do you see the thing around my face? Okay. The thing around my face is telling me, oh, look, that's a face. Okay. And do you see how it, like, I tried to trick it by changing, right? And then it's like, where's the, there's the face, right? Okay. And so it's blurring out everything else. On certain apps, certain devices, you can actually get a slider that will control the amount of blur that happens. And because this information is being captured by a LiDAR sensor, in modern phones, there's a light detecting and ranging sensor on here. You can actually capture depth information about the picture, and later in software, after the picture's been taken, you can actually slide the focal plane back and forth. You can change the depth of field and really blur out the background. Like modern photo tools are amazing. I am totally for them, right? Because they really simplify the work flow for taking pictures. So play around with the modes in your camera, right, for what it is that you want to do. Does anybody else notice what where'd the button go? Right there. Does anybody else notice what I've got on my screen that you may not have on yours? Do you see? I need a... we can see it better there. Do you see it? Do you see the grid? Yeah. Okay. So here's your added extra for today's lecture. I will give you this one free of charge. Okay? You want to take your photo. So first trick, if you're taking a picture of a person, what should you do? Portrait mode. Okay? Figure out how to do, it's called the bokeh effect. Figure out how to do that on your phone, right? Either manually or just with portrait mode, and let the device sort of figure it out, make it look good, okay? It's not a filter, by the way. Filters are post-processing effects that get added, right? This is we're actually using depth information to pull off something, okay? But I've got a grid on mine. You can find the grid settings, like on Apple devices, you go to camera, and it's one of the things, grid, turn it on or off. Right? Okay. Turn it on. Do yourself a favor, just turn on this grid and leave it. Okay. In Android, they have a similar setting. I just don't have a device to do it. Okay. What is that grid doing there? Do you notice how it's roughly split up the picture? How is it split up the picture here? It's split it up into thirds. This is something called the rule of thirds. Okay? In the rule of thirds, there are some intersection lines right here. Do you see where the lines that break it up, thirds top to bottom and thirds left to right, they intersect at these sort of center corners? The rule of thirds applies almost all the time, and guides you as to how to frame the subject of your photograph. Usually, you want to put the subject of your picture at one of those places where lines intersect. Let me see if I can't sort of explain what's going on here. Okay? If I take a picture of myself, without students in it, okay? Right? And I put myself dead center. Okay? Right? I get a picture. We'll look at that picture in a second. I'm going to subtly adjust the picture. Do you see what I did? Okay? Let's look at those pictures, right? I deliberately did two very different faces, right? Okay? Which of these pictures is actually more interesting? That one's goofier. But even with the dull face, right? This is physics face, isn't it? This is what you look like during lecture. Okay? Should we do another one so it's a little bit more fair? Okay. We'll do no students. Okay, there's that one. And then there's this one. An authentic selfie. By placing the subject at one of those places where the three lines intersect, you instantly get a picture that is psychologically more pleasing. Okay? Even though this one might be, ooh, post that one, Mr. Balogh, right? Okay. This one is intriguing the brain more. Simply by the location, right, of where I put my face, right? So you'll want to play around with the rule of thirds, okay, to see if you can't get something, right, that looks interesting. And you notice there were 4 places where those lines intersected, right? So you can move your shot around and change the sort of angle you're taking it at or whatever to try and get that rule of thirds. Your selfies will become more interesting. A lot of people take a selfie and put themselves smack dab in the center of the picture, right? Doesn't matter that I was in portrait or landscape mode, right? This rule of thirds applies to portrait pictures as well, right? Sticking your sort of center of your face at one of those top corners or maybe even one of the bottom corners if you're taking a picture upwards like this. Never take a picture this way. You guys know that, right? What happens if you take a picture this way? Double chin syndrome. Everybody looks fat, okay? When do you not look fat? Okay? When it's top down, okay? So if you want somebody to look bad, right? I can tell when the photographer at a wedding is trying to do a bad job or is an idiot, one of the two, right? And I just have to walk over and tap them on the shoulder and go, don't do that. They're like, whoa. I'm like, you're too low. Like, unless they were trying to, like, capture the bride's, like, the sunlight through the veil or, do a very specific shot, okay? If you're taking pictures of people, try to be up high as tall as you possibly can. I've been known to carry a ladder with me on photography shoots to make sure that I'm up high so that people look good, right? Or if we're going to set up a family picture, I'll make sure I'm uphill with the camera and everybody's downhill so that we can be doing that. So there you go. Simple ways to make all of your pictures look good. How does this thing work? Honestly, this is where it starts turning into magic for me. Okay? I am not a biologist, right? I am not a doctor. I just play one on TV. No. Wow. Talk about a structure, okay, that just amazes me. What does the eyeball do?
It gathers visual information.
It's even better than that. It captures electromagnetic waves, right? Your eyeball is your EM sensor. It's designed to capture electric and magnetic fields traveling through the air, through space, and then convert those fields into electrical signals that deliver not just depth information, but contrast as well as color. This thing rocks, right? So how does it work? Where does most of the focusing power of your eye come from? There's lots of structures in this picture, right? But there's only 2 of them that can focus light. What 2? The low-hanging fruit's the lens, right? Why is it called the lens? Because it's a lens. What kind of lens is it? Diverging or converging? It's a converging lens. You see how it's thicker in the middle, thinner on the outside edges, right? A lot of people mistakenly think that the lens focuses light. It does. Well, it does. It does a little bit. But it is not the primary focusing portion of your eye. Does anybody know what the primary one is? It's the cornea. Okay? The cornea is the thing that focuses most strongly focuses light in this setup. Because the cornea represents the biggest change in index of refraction through your eye. The index of refraction of air to the index of refraction of cornea, whatever that is, right? Okay, that's the biggest change. And so therefore you're going to have the most angled changes right at that interface. The lens and the cornea are pretty kind of close to each other, okay? It's a little bit of a difference. But that leaves the question, what is the lens for? If the cornea is doing most of the focusing, And our goal, right, is to get an image forming back here on the fovea, right, where all of our rods and cones and all those different cells are. What is the lens doing in our eye? Okay. At the risk of giving you a headache, too late, Mr. Balogh, okay, I would like you to do the following exercise, okay? I want you to take your fingers and just hold them at arm's length, okay? I want you to, again, be able to look across the room as far as you can, okay? Don't hit each other. I would like you to change what you're looking at. Look far away outside and then look at your fingers, and then look far away and then look at your fingers. And as you move back and forth, concentrate on the feeling in your eyeball. Far away, up close. Far away, up close. Can you feel what's happening in your eye? What's happening? Getting old. Can you feel the strain a little bit? We just did some squats, but for your eyeballs, okay? Your ciliary muscles that are attached to the lens, they are relaxing and constricting. Relaxing and am I using the right terminology, anatomy and phys people? I can't remember, okay? Right? And so they'll release, and then they'll go under tension, and they'll release. And as they tense up, what happens to your lens? It changes shape. It changes its focal length so that you are able to focus on things that are far away and focus on things up close. Last one, I promise. Put your hand out, fingers out, okay, at arm's length. Look all the way as far away as you can, right? All the way outside. Then switch your eyes to focus on your fingers, and then take your fingers and pull them towards your face and keep them in focus as long as you possibly can. Can you feel the strain? Okay. So when are our eyeballs the most tense? When we're looking far away or when we're looking up close? It's when we're looking up close. Up close for a normal eye that has no optical defects, meaning you don't need glasses or contact lenses or anything like that. Up close is 25 centimeters. About that far. Okay, it's called the near point. Okay. That means that a normal eyeball should be able to hold something about this close to the face and be able to focus on it. Anywhere closer, you might be able to focus, but there's a lot of strain, and eventually it just goes completely out of focus. Okay? How close do we operate nowadays? Pretty darn close, right? So as we're sitting here on our devices, getting neck strain and everything else, right? Check your posture, right? When you're working on something, right? Okay, right? Okay. But there's no escaping it. The problem is that if I try to hold my phone out here where it's a little bit more comfortable for my eyes, what's wrong? I can't, it's too small, right? Got to put old person mode on and get the text really big, right? Okay. What are we doing to our eyes all day long as we look at our screens? They're under when you take any muscle and you just put it under constant tension, what's it going to do? It's going to eventually cramp, right? Okay? It's going to scream. It's going to get into pain. People complain more and more nowadays about headaches, right? There's a lot of stuff going on. I'm not saying your headaches are caused by this, but a lot of us are straining our eyes all the time. So how do you fix it?
No more physics homework.
Yeah, no more physics homework. You guys know. No more reading. No. All it takes is 20 seconds every 10 minutes. 20 seconds, just look up, look across the room, look out the window, touch grass, do something, okay, that lets your eye relax. And to relax your eye, where are you looking? Far away. Actually, anything further than 15 feet's good. Okay? Just look far away, 20 seconds. Those of us who are attention deficit might look longer, but you know, right? And then you can come back to what you're doing. Every 10 minutes, look up. You're playing a video game? You got a natural spot between waves or something, right? Look up. And then you can come back to it. Okay? That alone will be enough to keep the tension in your eyeballs away. We will pick up with more of Mr. Balogh's health advice on Thursday when we start talking about glasses and contact lenses. We'll also do telescopes and microscopes. See you then. Oh yeah, I need all the magnifying lenses put back.